In section 2, we're going to work on evaluating polynomial functions using direct and synthetic substitution. Direct substitution you've already been doing, and you certainly already know how to do it. Synthetic substitution is something new, and it's a very important skill that we're going to use for a couple of different purposes in this chapter. Then we're also going to work on graphing polynomial functions. So you've graphed linear functions in Algebra 1, you've graphed quadratic functions so far in this course, and now we're going to move on to graphing higher degree functions. Key vocabulary in here in this section is going to be the concept of the polynomial, a polynomial function, synthetic substitution, and end behavior. End behavior is what a graph does as either end approaches infinity. So what does it do as the left end approaches negative infinity, and what does the right end do as we approach positive infinity? And we're going to go through that as we move through this section. So types of skills, the skills we use might be used to solve a problem like this. We've got information here about snowboarding from 1992 to 2003. Snowboarding actually is a pretty recent phenomenon. People used to ski with two skis, and surfers ended up sort of getting into the snowboarding thing. Certainly didn't do that when I was a young person. But the number of people who participate in snowboarding can be modeled by this function. So it's the number of snowboarders is equal to all of this. It looks like it's going to be a lot of fun to graph. S is the number of participants in millions, and T is the number of years since 1992. So you can see what that tells me is that in 1992, the 0 year, there are 1.2 million snowboarders, and then the amount will change as I plug in different values for t. So for 93, I would plug in 1. For 1994, I would plug in 2. And then we can go ahead and graph this model. And then we want to look at the graph that we make to estimate the first year that the number of snowboarding participants was greater than 2 million. Well, before we do that, we're going to go ahead and get some other information around. So in your vocabulary, polynomial is a monomial or a sum of monomials. And a polynomial function is a function in this form, f of x, meaning we're in function notation, is going to be the first leading coefficient, a sub n times x to the n power. The important thing you want to get here is, right, it gets a little confusing because they use so many things to represent what's going on. But the point you need to take away is that the degree, the exponent, the largest exponent is the first term. And the coefficient with that first term is the leading coefficient. So you can see that we go in descending powers as we move to the right, and we end up with the constant. Okay, so as long as you arrange your polynomials in descending powers of the individual terms, you're going to be okay. Okay, in this case, a sub n, the coefficient with the variable to the greatest power is called the leading coefficient. Whatever the greatest power is, that's the degree of the function. And a sub 0, the term at the end, is the constant term. So we're in standard form if its terms are written in descending order of exponents from left to right. And that's really what this says. It looks a little confusing, but you can see if my highest degree is n, then the next one is n minus 1, this would be n minus 2, n minus 3, and eventually we get to the first power, and the constant doesn't have a variable part, or you could say its variable part has an exponent of 0. So if we have a degree of 0, it's called a constant function. Here's what it looks like. F of x is equal to negative 14. It's a horizontal line. A degree of 1 is a linear function, so it's ax plus a sub 1 times x plus a sub 0, or we might talk about y is equal to mx plus b. You can see that b is the constant term. The leading coefficient m is the slope, and it looks like this, a linear equation. F of x is equal to 5x minus 7. If the degree is 2, this is what we worked on in the first chapter, it's a quadratic function. It has this form, and it might look like this. And as we move up in this chapter, we're going to be working with cubic functions and quartic functions. The key part is knowing that it's all determined by the greatest power of the variable. So if we want to look at these guys and see, are they polynomial functions, and if they are, to write them in standard form, state, degree, type, and leading coefficient. If I take a look here at number 1, I can see, okay, I have x to the 4th minus x squared plus 3. Okay, so I'm in descending powers. I'm in standard form. It's already there. It's quartic because it's to the 4th power, and it's already in standard form. That looks pretty good. If I take a look at b, I'm going to bring it on down here. It looks kind of okay, but it's not in the right order, so I'm going to write it in the correct order. I have pi x squared. Okay, pi could be a coefficient. That's not a problem. Plus 7x minus root 3. Root 3 could be the constant. That's not a problem. So this is a polynomial function. I'm sorry, I didn't write yes over here. Yes, that's a polynomial function. Yes, this is a polynomial function. Here it is in standard form, and it's quadratic. And I know it's quadratic because I have a degree of 2. If we take a look at this guy, 5x squared plus 3x to the negative 1 minus x, well, you could think, well, let me put it in descending powers. But I'm not allowed to have a negative exponent in a polynomial function, so the answer here is no. And in this final problem, number D, I have x plus 2 to the x power and minus 0.6. So if I try to start putting this into standard form, I'll have negative 0.6x to the 5th, right, plus x plus 2 to the x power. Well, this is not okay. My variable can't become an exponent, so no, this is not a polynomial function. So the key offending elements here for the ones that weren't was I can't have the variable becoming an exponent, and I can't have a negative exponent. Okay, and after that we work with identifying the type based on the degree, right? The degree is the highest power, and I didn't put down the leading coefficient. So the leading coefficient here is 1. I have 1x to the 4th. And the leading coefficient in this one is pi. Right? So leading coefficient here is pi. Here there's no number, but the number that is implied here is 1. Right? I don't need to put a 1 if there's 1x to the 4th. We just write x to the 4th and it's understood. So now we want to work on something called direct substitution. And direct substitution really just means I'm going to take a value for the variable and I'm going to plug it in wherever the variable goes. I am substituting it in directly. That's why it's called direct substitution. All right, so I plug this item in everywhere x is. So I'll have 2 times 3 to the 4th power minus 5 times 3 to the 3rd power minus 4 times 3 to the 1st power plus 8. And when I simplify this, I'll have 2 times 3 to the 4th power, which is 81, minus 5 times 3 to the 3rd power, which is 27, minus 12 plus 8. So this is 162 minus 135 minus 12 plus 8. So 162 minus 135 is going to become 27, I believe. Yeah, 27. Minus 12 plus 8. 27 minus 12 is 15 plus 8, and I just get 23. Okay, so direct substitution, you should be used to that as an idea. I'm not going to spend a lot of time demonstrating it. You've been doing it every time you make an input-output table. You pick values of x, you directly plug them into the function, but you can see the bigger these polynomials get, the less fun it is to plug those guys in. So what we're going to teach you now is an alternative to direct substitution, something that's called synthetic substitution. And what it allows me to do, I'm going to take the same polynomial. If you remember, right, I said that the value was going to be 23 when I did direct substitution. When I do synthetic substitution, I take the coefficients from my variable, from my polynomial function. And remember, let's go back and take a look at this function. It was 2x to the fourth minus 5x cubed minus 4x plus 8. So let's go back and write that in. 2x to the fourth minus 5x cubed minus 4x plus 8. Okay, and you'll notice that I'm taking the coefficients here, right? I take the 2 and I put it here. I take the negative 5 and I put it there. I take the negative 4 and I put it there, and I take the 8 and put it there. But why is this 0 here? Well, the 0 is here because I have to account for every power, right? So I had the fourth power, the third power, and then I didn't have a second power. So the 0 is in for the second power. So this is for x to the fourth. This is for x cubed. This is for x squared. That's for x to the first power. And this is for x to the 0 power, or the constant. So you see, I have to account for every one in its place. So when one is missing, I put in a 0. Okay, so this is just starting out. And then I'm going to take this value here, the 3. Here is the value I'm going to plug in. And then we follow a pattern. First we add downward. I'll have 2 plus nothing, which is 2. And I multiply it times this item. 3 times 2 is 6, and I record it in the next column. Then I add down. Negative 5 plus 6 is 1. And I continue to repeat this. So you see, here we are. Negative 5 plus 6 is 1. Times 3 is 3. I write it in the next column. 0 plus 3 is 3. Times 3 is 9. Negative 4 plus 9 is 5. Times 3 is 15. I put it in the next column. 8 plus 15 is 23. And I get the same value. Okay, so this pattern allows us to very quickly, without pulling out a calculator, very quickly pick values of x. We picked a value of 3, plug them into this function, and get out values of y, which will assist us in making an input-output table if we wanted to graph these guys. Okay, so for now I'm just going to demonstrate synthetic substitution for you again. The first thing I do is I pull down the coefficients. I have negative 2. I have 3. Now you'll notice there's no x squared, so I have to put in a 0 for x squared. I have negative 8x, and I have 13. The number I'm going to plug in is 2. So I add down. Negative 2 plus 0 is negative 2. I multiply times 2. 2 times negative 2 is negative 4. I add 3 to negative 4, and I get negative 1. Times 2 is negative 2. 0 plus negative 2 is negative 2. Times 2 is negative 4. Negative 8 plus negative 4 is negative 12. Times 2 is negative 24. 13 plus negative 24 is negative 11. And that's the value I would get. So if I were making an input-output table here, I'd have 2, negative 11. And I think you can see that the higher the polynomial's degree, the more I would prefer to do it this way, because it's just faster and easier, and it doesn't require as much work. Okay, same thing, but in evaluating this, you'll notice I don't have a fourth power. I have a third. I don't have x squared. I don't have x to the first power. So if I write this all out, and you might want to do this just to be clear, when you have missing powers of the variable, just go ahead and write them in with a 0 placeholder. Right? And you can see this is a 5th degree polynomial. That means I'm going to have 6 terms. 1, 2, 3, 4, 5, 6. I'll always have one more term than the degree. Here was a 4th degree. I have 1, 2, 3, 4, 5 terms. If I bring the coefficients down now, 6, 0, 10, 0, 0, negative 27. And I'm going to substitute in negative 3. 6 plus 0 is 6, times negative 3 is negative 18. Plus 0 is negative 18, times negative 3, that's going to be positive 54. Plus 10 is 64. (64) times negative 3 is negative 192, plus 0 is negative 192, times negative 3 is 576, plus 0 is 576, times negative 3 is negative 1728, plus negative 27 becomes negative 1755. Okay, now I don't know about you, but I think it's a lot easier to plug it in this way than actually putting it into a calculator and trying to figure out all these different parts. Okay, so to practice synthetic substitution, go ahead in your book and do problems 15, 16, and 17. Moving on, we're going to talk about end behavior. Now, end behavior is very helpful because, again, what it's talking about is what happens at the ends of my graph, right? What happens as I approach positive infinity? What happens as I approach negative infinity? Because practically speaking, as I'm looking at graphing these kinds of functions, if I know what's going on at the ends, that tells me when I can stop doing an input-output table. For instance, if I were to solve my polynomial, I would get these intercepts here. And I know that beyond the intercepts, the polynomial is just going to do whatever the end does. Once I know where all my intercepts are and I know what my ends do, I could look for this point and this point, and I've got a pretty decent graph of my polynomial. Okay, so instead of doing maybe 20 points to try to graph this polynomial, by finding its solutions, its zeros, knowing end behavior, and then finding values in between all the different x-intercepts, which are the solutions, I can do 5 points instead of maybe doing 20 points to try to graph this thing. So it's in my best interest to be able to identify what happens with end behavior. And what's important, there are two things only that are really important with end behavior, and that's the degree of the polynomial, right? The degree of the polynomial, and the leading coefficient. So now, the degree of the polynomial will tell you whether the ends do the same things or different things, and the leading coefficient will tell you what happens on the right end of the graph as you approach positive infinity. So, you will notice that when I have an odd degree, the ends do opposite things. My left end goes down, my right end goes up. My left end goes up, my right end goes down. The ends are opposites when the degree is odd. And if the leading coefficient is positive, then the right end goes up. If the leading coefficient is negative, the right end goes down. Since the right end goes down and it's odd, I know that the left end goes up. Okay? When we look at even degrees, like our quadratic function, right, it either opened up or it opened down. The ends do the same thing. And I know that if the leading coefficient is positive, the right end goes up, and since they do the same thing, that means the left end goes up too. And if the leading coefficient is negative, I know the right end goes down, and if the right end goes down, the left end goes down. Okay, so by looking at the degree and the leading coefficient, I can tell what happens on either ends of my polynomial, and that's a big help if I want to graph this with the least amount of work. So to practice identifying end behavior, go ahead and pause the video and work on problems 25 through 30, and then come back. Okay, so now I'm going to graph. We haven't really finished some of the important parts of what we would want to do, which is we would want to also talk about, as I was talking about graphing, we would also want to find out about, right, how do I find these solutions? We know a little bit from the quadratic section about how to find solutions. We're going to learn more about that. But for right now, I'm just going to do an input-output table, and I'm going to use what I know about end behavior. So I know that this is even, so I know that the ends do the same things, and my leading coefficient is positive. So even, and the leading coefficient is positive. That means that this end goes up and that end goes up. Okay, so if I want to go ahead and do an input-output table, I would go ahead and pick some values of x, and I would see what happens. The first one I'm going to pick is 0, 0, -2. So here's 0, -2. So I'm going to pick 1, and I'm going to make some observations about this because this is a very simple polynomial. When I plug 1 in, 1 to the 4th power is 1, -2 is -1. Well, so I'm at 1, -1. There we go. If that's true for 1, what would happen with -1? If I take -1 to the 4th power, it's also equal to 1. And when I subtract 2, that's also -1. So what's important for you to notice is that when I only have the variable going to an even power, I don't have to do a whole ton of these to know that if I plug in +1 or -1, the even power is going to make it end up be the same no matter what I plug in. So if I get a value for 2, it's going to be the same value for -2. So I plug 2 in, 2 to the 4th power is 16. 16 minus 2 is 14. And I know that's going to work for here and here. So really fast this thing shot up, right? So the 10, 14 would be all the way up here. And here's what's interesting now is this going to change at all? No. Right? So this is going to graph like a parabola because this is really in the same sort of form as a quadratic function. You could look at this as x squared minus 2, and this is actually a quadratic function. So there are certain types of functions, even degree functions, that will graph just like a quadratic function. So I knew I didn't have to do any other points on here because I can see that as I increase the value of x, it's just going to continue to increase. It's never going to turn back around. I know my end behavior says that both ends go up. I've got them going up, and I've gone far enough. So I really was fine with just graphing 5 points here really quick, and I've got the graph of my quartic function. Let's take a look at another one. So now here my degree is odd, and my leading coefficient is negative. So if it's negative, that means I know that this end goes down, and I know the ends do opposite things because it's odd, so I know this end is going to go up. Now if I go ahead and start picking some values, you're going to find me picking 0 a lot. When I plug in 0, 0 plus 5, 1, 2, 3, 4, sorry, 1, 2, 3, 4, 5, there's a point. I'm going to pick 1. 1 cubed is 1. The opposite of 1 is -1. -1 plus 5 is 4. So I'd be here. I'm headed back down. If I pick a -1, I'm going to see what happens going in the other direction. -1 cubed is -1. The opposite of -1 is 1. 1 plus 5 is 6. So at -1, I'm up here at 6. But I still don't have enough detail here for my graph. I can go ahead and continue to plug these values in, but I'm going to go ahead and use a technology tool. I'm going to go ahead and use my calculator. I'm going to plug this in and graph it. And then if I use the second function, I can use the second function with the graph button and pull up a table. And I can see that at -2, I'd have 13. At 2, I'd have -3. So what we're going to find here as we go forward, -2, 13 is way up here. And -2, or saying +2, -3, 1, 2, 3 is here. So you can see that this graph comes through here, kind of flattens out a little bit and heads down like this. Right? So it's a very, it gives this little wiggle in the middle. And normally when you have this, you'll see that I only have one solution, even though it's a third-degree polynomial. So I know there are 3 solutions. 2 of them are imaginary. So this little wiggle here comes from the 2 imaginary solutions. So when we're looking for 3 solutions, they don't always show up. So I have 2 imaginary solutions and 1 real, and that's why there's only 1 x-intercept on this particular graph. Okay, go ahead and practice the graphing doing problems 38 and 39. So pause the video and then come on back and we'll finish out the lesson. Okay, so now in doing this particular problem, I can see that it's going to help me a lot to go ahead and, again, use a tool like a calculator. If I plug this all into my calculator, I'm going to want to probably set my window very carefully. I only need values of x and y that are greater than 0, right? So I'm just working in quadrant 1 here. I know that this area of the year is from since 1992, so this would be 93, 94, right? 95, 96, 97, 98. This is 2000, and over here is 2002. And if I go ahead and plug this in, and again, if I use the second graph function, I'll get a table, and I can actually get an input-output table by looking at that. And it's going to help me a lot because I'm going to go through and graph, but I can see that these guys, 2, 3, 4, 5. So let's say that this is 1. Okay, so that makes this 1.2, 1.4, 1.6, 1.8, and this will be 2. And I did that because I'm looking at my values and I'm going, well, it's going to be difficult. I know that here in my starting year I'm 1.2. My constant would always come across here. And as I go across year 1, I'd be at 1.3, so right about here. At the second year, I'd be at 1.46, so right about here. Then on year 3, I go to 1.6. On year 4, I go just a teeny bit more, not quite 1.7. And then actually in year 5, it actually drops down a little bit again. In year 6, it drops down again. It's back to about 1.6. In year 7, it drops down. It's about 1.5. In year 8, it's about 1.44, so about 1.4 and a half, so maybe about here. And in year 9, it's going back up again. Now it's 1.55, so it's about here. And then we have a big surge in year 10, and it goes back up almost to 2 million. Okay, so this is our graph. If I had been plugging in, even with synthetic substitution, if I'd been plugging this in without using some sort of a technology tool, then I would have had a real difficult time doing this. But by using my graphing calculator and pulling up the table, it's very easy to do this. And they want to know, when did we get to 2 million? Well, we don't really get to, we get almost to 2 million in 2002. In 2003, we're at almost 3 million. So it goes way, way up over here. So the easiest solution here would be just about 2002. But by using the graph, it's pretty easy to pick the point where we hit that 2 million mark. And again, I use technology to help me do this. Now, I'm going to go ahead and post an Excel file that will do some synthetic substitution and a video to help you understand how to go ahead and use it to do that, to help make working with later sections in this book a little easier, a little quicker to go through the synthetic substitution. For now, do it by hand so you get a sense of how it works, and in later classes I'll tell you when I've posted the Excel file.